So today we're going to talk about using the Nernst equation. The Nernst equation is what we use to calculate voltages for electrochemical cells under non-standard conditions. And I said concentrations in a non-standard world because primarily we don't have solutions at standard states. We have them at some other molarity, and if you're calculating free energy or if you're calculating voltage, you need to take those things into account. You should all be familiar with this top equation. This is the equation for calculating the free energy under non-standard conditions. One of the things that I like to point out to people is that the Nernst equation and the free energy equation are essentially the same. The relationship between the Nernst equation and the free energy equation is just delta G is equal to minus NFE. That's a standard conversion that's true regardless of whether or not it's standard state or whether or not it's at non-standard states. I think some people get the impression that the E or G have to be under some particular circumstances. It's just a conversion that we can use to go from the units of volts as potential energy to free energy as potential work or the ability to do work. So if you take delta G and you divide it by minus N and F, this becomes E for the reaction, which is what we have down here. And if you take the rest of the equation, put minus NF and then minus NF, we end up with what we have here, E cell and RT over NF. And then we have ln of Q for the reaction. And if you remember, Q can be any number of different things, but it's the reaction quotient. It's that mass-action relationship between concentrations and equilibrium. And when we use Q, it's usually a diagnostic used to determine whether or not the reaction will go forward or backwards. But for free energy and for voltage, we can use this as a tool to calculate what the voltage you'd expect to see under non-standard states. Now, if you remember, standard conditions, 1 atmosphere, 1 molar, approximately, in solutions. And so if you have anything other than those concentrations, then we can calculate free energy or voltage under those conditions. One other thing I wanted to make a note of, we often, and there really is no difference, we use the word cell, and we use reaction, and there really isn't any difference between cell and reaction. We're talking about a cell reaction. That is, we take one half cell and another half cell. We're taking one half reaction and another half reaction to produce a full reaction. It's the same thing as delta G of reaction. You could call it delta G of the cell as well. So let's look at our first non-standard cell. What we're going to recognize, first of all, is that these are non-standard conditions. This is 0.25 molar, and this is 1 times 10 to the minus 4 molar. So that's what you recognize as being something different in the problem. And what you have to do next is you have to write the redox reaction from the cell notation to determine N and E0 from the balanced reaction, and then you write Q and you plug everything into the Nernst equation. Here's some data. We'll go ahead and use that on the next slide and we'll work the problem out. Okay, so I have zinc on the left and I have silver on the right, and if you remember the way this notation is done, we always write the left side of the cell notation as the anode and the right side as the cathode, which means the left side of the reaction we've got to write as an oxidation. So what did we write when we write the oxidation of zinc? We write zinc solid, I'll leave that state out, to zinc 2 plus, which is aqueous. And again, I'm leaving that out, and we can fill those things in later if we need to, plus 2 electrons. And then on the cathode side, which is the reduction side, we write the reduction of silver. That is, we go Ag plus 1 electron gives me Ag solid. And then we look up those cell potentials, and I looked them up already. The silver is still written as a reduction, so that's 0.799 volts. And the zinc is now written as an oxidation, so you write that as plus 0.762 volts. And just one bit of warning, many of you are familiar with this equation that the cell potential is equal to E anode minus E cathode. If you flip the reactions and change the signs, then you don't use this equation. That will completely give you the wrong answer. So now what you do is you simply add those two half cell potentials up, and you come up with 1.541 volts. By the way, if you download my notes, if you're in my class, you can download my notes, and all this is typed in the bottom of the slides, along with some other things that I say about the reaction. Okay, so we're going to add those two. We added those two voltages. We have to add these two cells, so we need to put in the appropriate coefficients, and I didn't leave room, so that's times 2 on this side, and we're going to have 2 here, and that will become 2 electrons, so that when we add these two, the electrons will cancel, and my overall reaction is 2Ag plus Zn make Ag, 2 Ags plus Zn2 plus. Now, a couple of reasons it's important to go through this process, go through this exercise. One, we need to know what N is. This is N. N is the number of electrons in the balanced reaction. And so we'd say there's 2 equivalents of electrons per mole. Oops, left my 2 out. 2. And we also need to be able to write a reaction quotient, and you can't do that unless you know how it's balanced. Now, we leave the solids out and the liquids out, but in this case, we can write Q as the concentration of the products to their coefficients divided by the concentration of the reactants, which in this case is silver. And there's 2 of them in the balanced equation, so we square that. So there's Q. Now we're all set. We can plug it into the Nernst equation. And just as a reminder, the Nernst equation is E is equal to, and that cell is E0 of the reaction plus RT over NF ln of Q. So I'll go ahead and write Q in. And now we can start plugging in our information. E cell, the standard cell potential is 1.541. Units are volts plus units for R 8.314 joules per mole times Kelvin times 298 Kelvin. Now, why did I choose 298 Kelvin? If it doesn't say what the temperature is, it's done at the temperature of whatever the data in the tables are at, and that's generally 298 Kelvin. But that's not a standard, so sometimes you'll have to check these things. Now for N, it's 2 equivalents per mole. Save a little space by writing like that. That's per mole of reaction, and then it's Faraday's constant, which is 96,485 coulombs per equivalent, times the natural log of Q, which in this case, if we look at our concentrations, the concentration of zinc is 0.25 molar, divided by the concentration of silver, 1 times 10 to the minus 4. squared. Now, just to break this calculation down for you a little bit, but you don't have to do it this way, it's going to be 1.54 plus 0.2187, and that gives you 1.76 volts. That's one very common example of the Nernst equation where you have to calculate the voltage under non-standard states. This is known as a concentration cell. Now, in a concentration cell, all that's different in the two half cells is one's written as an anode, one's written as a cathode, and that you have a difference in the concentration of the metal ion in solution. That is, I have a copper half cell as both the anode and the cathode, but I have different concentrations. You'll recognize this simply by seeing that it's the same reaction at the cathode and the anode. That is, copper goes to copper 2+, and copper 2+ goes to copper solid. Don't get confused by looking at these molarities at first. Just look at what species are in the solution, and that's what reactions you'll have to write. So when you write these reactions, what you need to do is you need to keep track, that is down here, you need to keep track of the overall reaction, and the overall reaction is going to turn out to be kind of odd. It's copper 2+ that goes to copper 2+. The difference is one is copper 2+ in the anode cell and one is copper 2+ in the cathode cell. Really important that you keep these things straight, and I always give subscripts as A and C for anode and cathode as I write them. When you're done with that, then what you can do is you can write out the correct expression for Q, the number of electrons you'll take from the charge of the ion, if it goes to the metal. If it goes to some other ion, then you have to take N as the number of electrons to go from one charged species to another. Let's say, for example, tin 4 to tin 2 N would be 2 as well, but tin 3 to iron 3 to iron 2 N would be 1. Okay, so let's go ahead on this next slide and let's work out this example. On the left-hand side, we need to keep track of the anode and the cathode. So on the left-hand side, we have to keep track or keep in mind that this left side is the anode. So what is the anode? The anode is oxidation. So we'll write our oxidation reaction. Cu goes to Cu2+ at the anode, plus 2 electrons. And then you can write for the cathode, it's the same reaction, but it's written as a reduction. So it's Cu2+ at the cathode plus 2 electrons goes to copper. Now, if you hadn't kept track of the anode and cathode, when you go to add these two reactions up, the coppers go away, the electrons go away, and if you haven't kept track of anode and cathode, copper 2+s would have gone away too, and you would have had nothing left. So the overall reaction now becomes Cu2+ from the cathode goes to Cu2+ at the anode. And I can write Q from that as the concentration of copper at the anode divided by the concentration of copper 2+ at the, and that's a 2+ up there. Copper 2+ at the cathode. And if you remember right, that's the cathode and anode, so those are the concentrations respectively that I'll be putting into the expression. There's the anode, cathode concentration and the anode concentration. It's always a little bit confusing to understand what E cell is for this reaction. Remember, E cell is the standard cell potential for this reaction. So standard cell potential means standard states. Standard states means 1 molar concentrations. If it was a gas, it'd be 1 atmosphere concentration. Now, in that case, then copper 2+ at the cathode and copper 2+ at the anode are exactly the same. In other words, you can get rid of the subscript and then everything does disappear. If everything disappears, that means E0 for the cell is 0. That is, it's a concentration cell if the concentrations on the left side and the right side are the same. all the terms drop out when you cancel it out, and cell potential is 0. You still have to keep track of the fact that N is equal to 2. So that's 2 equivalents per mole of reaction. And now I can write the Nernst equation out. So remember, the Nernst equation will be E cell is equal to 0, that's the cell potential for the standard, plus RT 8.314 joules per mole Kelvin times 298 Kelvin divided by N. Now N is 2 equivalents per mole. And F is 96,485 coulombs per equivalent. That'll be times Ln, and in this case, 0.10, that's my anode concentration, divided by 1 times 10 to the minus 12. You plug all this into your calculator, and what you get is negative 0.296 volts. Kind of an interesting side note, if you think about what this voltage means, this is non-spontaneous for this reaction. And if you think about what the concentrations are, the cathode concentration is 1 times 10 to the minus 12, and the anode concentration is 0.1 in molarity units. So what this equation actually says is that a more dilute solution will not become more concentrated by itself. That is, that's the direction of the non-spontaneous reaction. The voltage turned out negative. Remember, negative voltage means non-spontaneous. Positive voltage means that the reaction is spontaneous and that you'd expect some forward movement of the reaction. Well, we have one more example to cover, and it ties in really well with what you learned at the end of the solutions or the aqueous chemistry section on solubility products. Here we have a problem, and what you have to recognize in the problem is that you have this second solid in the solution besides the electrode. And if you look at this, this is something that you would expect to precipitate out of solution, and this is one of the precipitating agents for it. On the other side, you have the metal ion by itself at a non-standard concentration producing copper solid. So what we need to do is we need to write this reaction out and interpret it in terms of what it is. And I'll just sort of cut to the chase, as they say in English. When you write out the redox reactions, you'll write out the cell equation and use KSP. You use the Nernst equation and KSP to calculate the cell potential. What you'll find when you write out the reactions is this reaction is closely related to the solubility product. It'll either be the solubility product equation, that is the solid being dissociated into its ions, or it'll be the precipitation reaction where the ions are forming into the solid. And based on that, that's what you use to write out your KSPs, or your equilibrium constants, and then from the equilibrium constants, you can calculate the standard cell potential for a precipitation reaction. So let's work this out on the next slide. What we have is a anode, which is a little trickier now. What's being oxidized? And it has to be, in the anode case, the solid going to Cu plus. Now, where did I get the plus from? It's with I minus, and there's one of them, so it must be plus. Now, you'll notice this reaction is not valid because I have that. And I have this other thing in solution, the precipitating agent. So what you write is you write the following. You say Cu plus I minus makes Cui, and then you charge balance it. There's one electron on this side. That is the anode reaction. You can think of it as happening in two steps. That is, you have Cu going to Cu plus, and then you have Cu plus I minus going to make Cui. This top reaction is a redox, so I go like that. When I add these two together, the Cu pluses will cancel, and then I'm left with this reaction. Okay? So you write the oxidation of the metal, you fiddle around a little bit to figure out what you need to add to the reaction to get the solid, the precipitate, and then once you've figured out that and you add them together, you can pretty easily obtain the half reaction for that particular anode. Now the cathode side's relatively easy. On the cathode side, it's just Cu plus one electron goes to Cu solid. And then when I add these two together, I do the following. Cui minus makes Cui plus 1e minus. Add these together. The electron goes away. The copper solids will go away. And you have Cu plus I minus makes Cui. Now I find this to be relatively fascinating because we don't think of that as a redox reaction, but because it can be written as half reactions, we can in fact measure solubility products using redox reactions. Now, that is not exactly KSP reaction. That's the inverse of the KSP. So, K for this particular reaction is equal to 1 divided by KSP. So if I want to calculate the standard cell potential for a precipitation reaction, I go back to the equilibrium equation for the Nernst equation and just say E 0 cell is equal to minus RT over NF natural log of I'm sorry, that's plus RT over NF, natural log of K. And in this case, K is 1 over KSP. And that voltage comes out to 0.3535 volts. So that's E0 for the cell, and now I can use the Nernst equation to calculate what the potential of the non-standard cell is. I'm going to use E cell is equal to 0.3535 volts plus, ran out of room, plus, I'll just write it down here, RT over NF times the natural log of, and this is actually 1 over QSP, but if you look at the reaction as it's written, it's products, which are solid, divided by reactants. So it's just going to be 1 over the concentration of the copper times the concentration of the iodine. If I take the numbers given in the problem as 0.01 and 0.01, you find that this portion of the problem is equal to 0.1182, and the overall voltage is that is the cell potential, is 0.472 volts. So I hope that helps you with your problems and using the Nernst equation under non-standard conditions and with some of its applications.